So far in this atomic physics unit, we've really been focusing primarily on the nucleus and what happens inside the nucleus, the protons and neutrons changing to create new elements. Well, another aspect of atomic physics is focusing instead on the electrons. We haven't looked at the electrons yet, but the electrons are responsible for a lot of different things, including light. So let's talk about electrons and how they can produce light using something called the atomic spectra. Now, we have talked about light before in our waves unit in this class. Light is just energy, and light specifically is important because it can be treated as a wave or as a particle. You can think about it in both ways, and actually, it is both things. Light is both a wave and a particle. We call it the wave particle duality. In this example, though, we are going to look at it primarily as a particle, specifically a photon. So you might know of light particle being a photon that is going to be important to us is basically just a packet of energy carrying energy from one place to another. Now, light is quantized, that these photons can only have certain discrete values of energy. What that means is that you can have energy here or energy here, but not these energies in between, this quantized discrete values. And to get us to understand that, we're going to see it in a couple different ways. It primarily comes down to the different energy levels that an atom can have and the electrons can take on. But we can see it in a couple different ways mathematically as well. First, we'll see it in this equation here. This is the equation to help us calculate the energy of a photon. Here, energy is presented in a capital E. Energy is always in units of joules for the time being. You'll also see Planck's constant. This is a new constant for us. It's 6.63 times 10 to the negative 34th joule seconds. This constant is in your data booklet, and it's basically our multiplier here for us to be able to turn frequency in hertz into this energy in joules. That means that the higher the frequency the light is, the higher the energy the photon is carrying. We've seen this in our light unit as well. Something like X-rays are very high energy electromagnetic waves because they have a high frequency. The high frequency translates to a really high energy. Now, this isn't the only equation that you could use. If you wanted to, you could also relate the energy to the wavelength. We remember that our wavelength is represented here in this equation. C is equal to F lambda, C being the speed of light, and lambda being the wavelength. If I rearrange that to solve that for frequency, frequency is just speed of light divided by wavelength. And then I can substitute that in for my frequency here. So the energy now, instead of being Planck's constant h times F, it is now h times c over lambda. If I rearrange that or kind of combine things, I can see that lambda ends up being hc over e. Um, so it's just another way of representing that by smashing these two equations together. C, by the way, you probably know at this point already, but it's in your data booklet, is 3 times 10 to the 8th meters per second, speed of light. So that was how to find the energy in joules. Well, that isn't the only energy that we're going to be using talking about atomic spectra and specifically in atomic physics as a whole. We are also going to use this other unit of energy called electron volts. We saw electron volts. We were talking about mass defect as well, specifically mega electron volts. Well, here for electron volts, this is a unit of energy, and we can convert between joules and electron volts with a simple relationship that the energy in electron volts is just the energy in joules divided by the elementary charge. Elementary charge in the data booklet is 1.6 times 10 to the negative 19th, which means the energy in electron volts is always going to be a bigger number than the energy in joules. It is a much finer measurement compared to joules. All right, let's find all of this in the data booklet. Subtopic 7.1 has these two equations relating energy to the frequency and wavelength of light. You'll also see some variables here that were useful. Speed of light in a vacuum, that's C, Planck's constant, H, and then the elementary charge if you're trying to convert electron volts into joules or vice versa. All right, let's see this in action. If I have this equation here, I'm rearranging that second equation, the one that's presented as lambda is equal to hc over e. I just rearrange that to solve for E. E is equal to hc over lambda. I want to calculate the energy carried by one photon of microwaves of wavelength 9 centimeters. Um, Now, we want to do it here in both joules and electron volts. So I can plug in to figure out that energy. I will need to use the wavelength in meters instead of centimeters. So I'm going to convert that, just move the decimal over 2 times because there are 100 centimeters in a meter. Plugging that in, h is 6.63 times 10 to the negative 34th. C is 3 times 10 to the 8th. Divide that by lambda, 0.09 meters, and I get 2.21 times 10 to the negative 24th joules. That's a very small number of joules. So a more useful measurement might be in electron volts. Well, to convert that to electron volts, I just need to divide it by 1.6 times 10 to the negative 19th. Doing that, I get 1.38 times 10 to the fifth, or negative fifth, electron volts. So again, all I'm doing here is I'm just trying to find the energy that corresponds to this kind of light, specifically at this wavelength. It'll be this many joules and this many electron volts. All right. One of the things that you might notice here is H and C, they're both constants. Anything H times C is going to give you the same number because they're always the same number. So there is a shortcut in the IB Physics data booklet under the unit conversions page for whatever reason. You will see this shortcut HC. HC is this same HC. It's Planck's constant times the speed of light. And in this part of the data booklet, that multiplication has already been done for you. If you took that 6.63 times 10 to the negative 34th and multiply it by 3 times 10 to the 8th, you will get 1.99 times 10 to the negative 25th joule meters. It's also given to you in electron volt meters. And that can be a nice shortcut because if I took this and use that first uh, example, 1.99 times 10 to the negative 25th joule meters, and divide that by the wavelength that we used in the last problem, 0.09 meters. The meters cross off, and I'm left with joules, 2.21 times 10 to the negative 24th joules. That is the same value that I had before. It's just a little less work. I don't have to multiply those numbers together. It's already been done for me. If instead I wanted to find electron volts instead of joules, I'll just use that second value. 1.24 times 10 to the negative sixth electron volt meters divided by 0.09 meters. The meters cross off, and I'm left with 1.38 times 10 to the negative fifth electron volts. So compare that to the work that we did in the last slide. That's quite a bit less. It saves us multiplication of H and C, and it saves us a conversion from joules to electron volts. We can go straight there by using this nice shortcut. All right, so that is all background to help us understand how this light is going to be produced and how to predict where it's going to be. So you might know from your chemistry days that electrons in an atom exist at these certain discrete energy levels. You can um, send some energy. It can be absorbed by an electron, and that absorbed energy allows the electron to promote up to a higher energy level. That higher energy level electron can sometimes also then drop back down to be in a more stable state, closer to its ground state. When it does that, it emits some energy. So these electrons can either absorb or emit. But the thing is, the amount of energy that is absorbed or emitted corresponds to the different energies at these energy levels. And we can see that with a certain number of energy levels, there are only a certain number of transitions that could theoretically take place. Here, if you have 1, 2, 3, 4 energy levels, you could have an electron drop down from 4 to 1, or from 4 to 2, or from 4 to 3. You could also have an electron drop down from 3 to 1, or 3 to 2, or you could have an electron drop down from 2 to 1. All of these are different energies. So we need to know that there are 6 possible energy level transitions dropping down from higher to lower. Obviously, if you had counted the absorbed energy levels too, we would get 12 because they go both directions. But here, let's just look at the different transitions that have different amounts of energy differences. And how you'll typically see this presented is instead of being kind of in that curved orbital sort of structure, you'll see these energy levels presented as just a series of stacked lines. The farther the spacing, the bigger the energy difference between them. And you'll notice here we have a bunch of energy levels that are above the energy level of state one. We call these excited states. And then one is our ground state. You'll also notice here that there are energies assigned to these. Zero is treated as our freely liberated electron. And then the energy levels below that actually have a negative energy. This is the amount of energy that's required to input to the electron to free it, to ionize that atom and liberate that electron. So don't get too stressed out about that negative in there. All we really care about in the end is going to be the energy difference anyway. So these energy transitions will result in different amounts of energy. Sometimes we can categorize them because these different amounts of energy result in different types of light. If we, for this particular atom, dropped all the way down to the first level, that results in light of a pretty high energy. Notice how long those drops are, how big that energy changes. These are going to result in light in the UV ultraviolet spectrum. The Balmer series here is visible light, and the Paskin series is infrared. You don't need to know these. It just helps to see kind of how these relate because it's more than just light that we're able to see with our eyes. Other electromagnetic waves are being produced just outside of our own visible range. And if you took white light and pass it through a prism or another way to bend light, like a diffraction grating, you can disperse its light into its component colors. You probably know a little bit about this as a way of seeing a rainbow. Well, that is true with white light. You can see that full rainbow spectrum, but it is not true with an element producing light through its atomic spectra because in that atomic spectra, only certain wavelengths of light are produced because only certain energy drops are being represented. And our way of seeing those different wavelengths is by passing this light that is produced in a certain emission spectrum of an element and passing that through a prism to separate out the color, similar to how we would do for a rainbow. But instead of seeing that continuous rainbow, we are only going to see these discrete lines that are representing certain colors of these energy drops. So here we see a red, a blue-green, a blue-violet, and a violet. And different elements have different energy levels and will have different transitions that result in different colors. These are basically like a fingerprint for the element. We'll see these later on. They're called line spectra. They're really important in the world of astrophysics as a way of identifying what elements are being produced in a star. Just by looking at that star, you can see the spectra and understand the elements that are involved. You can also have something called an absorption spectra. An absorption spectra is when you take white light, so something from a hot source just glowing like an incandescent light bulb, and pass it through a gas. Well, just like these energy transitions can drop down and emit light, as we saw, they can absorb light, move up, and then store that energy. When they absorb that energy, it results in basically the negative of that emission spectra. So, an emission spectra and an absorption spectrum are slightly different. You see it just showing up as individual lines of light for an emission spectrum. An absorption spectrum is a whole spectrum, the whole rainbow, with these kind of gaps in that spectrum. But they always will result in the same corresponding wavelengths. Okay, so you can see this showing up. This is one of my favorite XKCD, well, one of many, showing the whole electromagnetic spectrum and absorption spectrum has a little nod there. All right, so let's see what the math is involved in this. If I have an energy transition going from 3 down to 1, the corresponding energies are going from negative 1.51 electron volts to negative 13.6 electron volts. My difference there is the energy that is going to be carried in the photon that is leaving that atom. So that energy difference is 13.6 minus 1.51, so 12.09 electron volts. I don't really care that they're negative here because it's the difference that I really need to know. So you'll see that I'm not really acknowledging the negative. I'm just finding its delta. Then we know this equation from before. Lambda is equal to hc over E. I know what E is now, and I know some values for hc. Remember, this is that shortcut that I found in the unit conversions part of the data booklet. I'm going to use electron volt meters because I have an energy that is already in electron volts. By doing so, the electron volts cancel. I'm left with 1.03 times 10 to the negative 7th meters, which in nanometers, if I were to multiply by 10 to the ninth, would be 103 nanometers. Typically, kind of a good rule of thumb is that if you're talking about visible light or close to visible light, you're going to be having a wavelength that's in hundreds of nanometers. So somewhere between 100 and 900 nanometers is where you'll find the visible light part of the spectrum. So let's see another example here. Let's look at a transition from 4 to 2. Again, same idea that I can find that energy by just comparing where it started and where it ended. My total energy is 3.4 minus 0.85, so 2.55 electron volts. I can take that energy and plug it into this equation to find lambda is 4.86 times 10 to the negative 7th, or in nanometers, 486 nanometers. So if you're trying to figure out what wavelength is produced by a certain energy drop, just find the energy and then translate that energy into a wavelength using this relationship. I could do this many different times. Every possible drop will have an energy, and I can calculate that energy, and I could take that energy and calculate a wavelength, and I could assemble by hand what I would expect the atomic spectra to look like. So find those lines by figuring out every wavelength that's represented by the different energy drops. I can also take this and go the opposite direction as well. If I start with a wavelength, so in this case, I start with blue light that is 434 nanometers, I can take that and go backwards. If I take that as my wavelength, I can rearrange this formula and I can convert that wavelength from nanometers into meters. 434 times 10 to the negative ninth meters. That's just kind of a shortcut way of doing it to tack on that new magnitude. Now, if I rearrange this formula to solve for E, E is hc over lambda. I'm going to plug in that meters for lambda, 434 times 10 to the negative ninth, and I'm going to use my hc value, my shortcut, using electron volts again. That is more commonly seen in these atomic spectra, energy level charts. You might also see joules in there, and if so, use the one that's joule meters to be a little bit shorter and easier to get to. If I cancel out the meters, I end up with just electron volts. Just electron volts will give me 2.86 electron volts. All right, so that's interesting, but not super useful yet. Here, all I did was just convert wavelength back into energy. But now to finish this off, there is only one energy transition that will result in 2.86 electron volts. So you might need to guess and check, but you should be able to figure out, kind of Sherlock Holmes your way into figuring out what the energy transition is that will result in a difference of 2.86. Well, in this case, that is energy level 5 down to energy level 2 because 3.4 times, or 3.4 minus 0.54 is 2.86 electron volts, which we calculated before is the energy that is associated with the wavelength of 434 nanometers. All right, in this video, you should be comfortable with these different equations. Calculating, let's go all the way back to our equations here. Way back, you should be able to calculate all of these different energies and how it corresponds to the wavelength and frequency of your light all the way back here. You should also be able to use this understanding to predict these energy transitions and how it corresponds to the energy or vice versa.